give you key ideas and paradigms that we used as basis of a solution for testing big data pipelines on our laptops without relying on any third-party additional tooling, which come with its price tag, of course. And most importantly, they could be kind of a closed source. Hope I could give you enough knowledge and encouragement so you could develop something like this yourself. Well, I mentioned big data, and because I know it's kind of a buzzword, I just wanted to be sure we are on the same page. So let's clear up what is a big data. Well, whenever I talk about it, imagine something and data that is so large, fast, and complex that it is difficult or impossible to process using the traditional data processing application software. I believe all of you at least once have worked with the traditional relational database management systems. They would most commonly consist of one very packed server, like with a lot of CPUs, SSDs, RAMs, and etc. And they would be more suitable for transactional processing systems. They can handle thousands of transactions and a lot of data modification queries, like update, delete, additions, and etc. But sometimes we have other use cases when working with data. We need to run complex and very expensive queries with a lot of aggregation, analytic functions, queries that require full table scans on tables having millions and billions of rows. So the traditional databases are not up to this task. And that is why for the past 10 years, to solve this problem, the distributed query engines were in development. Example of them you could see at the bottom right, like Hive, Spark, Presto, Flink, and etc. And they are distributed because the queries are executed over a cluster of nodes. We normally call them worker nodes. And each node is going to execute the query over a smaller subset of the data. And later on, a master node will combine the results for the final results. And why am I saying this? We have the solution for the problem, yes, but we are using these engines to build pipelines. And another problem appear, how are we going to test these pipelines? So let's take a look at an example. For simplicity, let's have a code base with one batch job that is written in Java, and we are going to leverage SQL to work with the data. This application will be deployed in the cloud with a CI/CD pipeline, and our job is going to be executed over a Spark cluster, which is basically what is basically Glue. We are going to work with 8 terabytes of data, which means that our job will execute for few hours. And because in the cloud we pay for the processing, we are going to have additional costs for that. Anyway, our job is going to prepare a report at the end, and we are going to expose the results in a dashboard, in a BI tool, like Tableau mode or whatever. So these dashboards and visualizations will be used by different stakeholders to take different business decisions. And imagine I'm the developer of this bad job and I made a mistake in my SQL query. If I find a way to test this early on while I'm in the development, it is going to cost me only, depending on the problem with my query, only a few minutes to a few hours to fix this bug. Because I will modify the query, I will rerun my pipeline locally, and I will be able to fix it. But if I'm not able to test it locally and I need to deploy it somewhere in the cloud, in dev environment, for example, it is going to cost me again time, even additional time. So because I need to wait for the whole CI/CD pipeline to deploy my job somewhere in the cloud. but it is going to cost me money because, as I said, my job will run for a few hours and I will need to pay for this processing in the cloud. Anyway, how much is it going to cost me if I find the bug at the latest stage? Well, of course, all of these things that I already explained, they will be applicable for the latest stage, but another possibility that could happen and another consequence is that this wrong data could be used by our stakeholders to make bad business decision. So we understand that the later we find the bugs, the more time consuming and the more costlier they become. And they could lead us to make bad business decisions. And we actually even can't estimate and predict how much this is going to cost for us. So having all of these in mind, we set different goals for our solution. We wanted it to be locally testable on the developer machine in the phase of when they're developing the pipeline. I explained why in the previous slide. We wanted to make our lives easier, so that's why in the perfect case, we wanted this solution to, we didn't want to make a lot of effort to set up our testing environment. So in the best case, the developer would only need to set up Java, install his favorite IDE, and then take the project, check out the project locally, and he will be good to go. Of course, we wanted our solution to be integratable with a CI/CD pipeline. We wanted it to be technology agnostic because we didn't want to tie to any specific provider or their technology stack. Our reasons are because if a new technology that is going to be better for us, like it would provide better processing or storage, we wanted to be able to migrate to that technology. And on the other hand, because requirements changes very, very quickly, we wanted to be able to migrate from on-prem to cloud and vice versa. So, and last but not least, we wanted our solution to be cost and time efficient, to help us very fastly and easily implement and test our pipelines locally, and to not generate additional cost when we want to scale. So having said all of those goals in mind, we started looking for the different options, and the natural first step was to look at the already existing solutions. One of the possibility was using LocalStack. It was going to meet some of our goals, like testing locally and automatically early in the development stage. We were going to have it very quickly up and running. However, this was going to bound us to Amazon. And this was not going to fit one of our goals, to be technology agnostic and migratable. And that was the biggest problem with the existing solutions, that they are emulating cloud-specific technologies and they do not target more than one service provider and their technology stack. So another reason we didn't choose the ready solution is because they do not always target the SQL pipeline. So for us, this meant that we needed to bootstrap additional services, and these come with additional cost. And the cost was going to increase the more we scale our solution. The more pipelines we have, even the more developers, because some of them are subscription-based, and the more users we have, the more we were going to pay. So obviously, this wasn't fitting to our goal to be cost efficient. So that's why, to meet all of our goals, we developed the so-called SQL Library for running and unit testing SQL-driven workloads in an engine-agnostic way. To be able to achieve this, we based our solution in few very important key pillars. First of all, we needed to provide local emulation of the different analytical engines. This was going to give us the ability to test our solution over multiple engines in advance. And later on, if you want to migrate, this was going to happen without a lot of changes in our code base. Another thing, in our pipelines, very often we need to perform different file operations. So that's why different file operations, and our project and our pipelines were going to run in the production environment over a distributed file storage. But in order to be to work locally, we were going to use the local file system. So that's why we provided a common API to simulate all of the interactions that we would normally do in production over S3 or Azure locally. And last but not least, because we needed to provide, because we needed to execute a lot of queries over different multiple engines, we needed to provide a way to write engine agnostic SQLs. And of course, to be able to execute SQL queries, and each of these engines have different differences in these submissioning details. They use different protocols and different APIs. So we needed to think about that. Let's take a look first at the way we implemented the local emulation aspect. First of all, I know there's a lot of different technologies that you see here. I know how difficult it is to differentiate all of them, but like imagine each of them has, they all have similar functionalities and functions, but each of them is appropriate for different scenarios and need to perform better in different use cases. Just a quick example, Spark and Flink, they both support streaming and batch processing. But if I need to stream live data with a very low latency, I would most certainly use Flink. On the other hand, if I wanna perform batch processing and I don't have a requirement for the latency, I will choose Spark. Anyway, all of them has specifics, and we were able to emulate them in two different modes, embedded and external process mode. In embedded, we are leveraging Spark and Flink's local execution mode, and we run them as part of our application. Their clusters are running in the same JVM as separate threads. Anyway, we couldn't find a proper way to do that with Hive and Presto, so that's why we had the idea to store them as external processes in the operating system. And of course, this requires additional work like downloading the executables, storing them somewhere, the installation part, starting them in specific order, and for all of that is handled by our framework. So it is going to be very convenient for the developer to start them. He doesn't do anything. And we achieved all of these by only using Java, only setting Java on our machines, no additional software, no containers, and so on. So as I mentioned, we needed to be able to perform different file operations. Let me give you an example. We need to prepare file partitions, or sometimes we need to group files together so they could be registered as one table, and so on. So here you see a small subset of the different file operations that in general exist, but this is sufficient for us and for our needs when we implement our pipelines. And that's why we call it a minimal file system abstraction. And down here, you see the specific implementations. So whenever an URI schema is provided here, the framework is going to switch between the local or the production implementations. And in that way, we are providing for a developer, a common way to work with the file system without worrying for the, file specifics that he's working on. And last but not least, I mentioned that we needed to be able to execute queries, and not only that, but over different engines that have different submissioning details and have we use different protocols and APIs and etc. So that's why we have another abstraction about this. We are executing queries without results, and another thing that we need is to execute queries and store the results. So that's why we have an abstract representation of the result. Here again, you could see the specific implementations of this executor. For example, this one is going to use the JDBC protocol. This one is going to use directly Spark's job submission API to execute queries. This one could leverage the AWS client and so on. So whenever we choose an engine, we are going to switch between these different implementation. I mentioned engine agnostic queries. How do we achieve this? How were we able to write that type of queries? Well, we have another abstraction over the dialect specific for the different engines. And we have a templating mechanism. So we are able to write a template and later on to generate from that template SQL queries that would run perfectly over the different engines. So after having all of these bases provided by our framework, we needed to sit down and write our unit test, right? So to do this, we follow a few testing best practices. First of all, we are very careful when we are starting our engines, because especially the ones I mentioned earlier, where are started as a separate process, they could be very heavy and they could have long startup times because they require a lot of extra work. So whenever we are testing with them locally, we are having a caching technique. We don't always, download them and install them and etc. We only do that whenever we have a newer version of them. Another thing is that sometimes it would be more than sufficient to test only against a few of the engines. So we don't need to initialize the other one. We are initializing only the ones we are using. Of course, our test should be atomic. Whenever a test is starting, they need to prepare all of the data, all of the tables and schemas that they need to perform their assertions. At the end, they need to clean up after them. And there shouldn't be a specific run ordering between the tests, and they shouldn't rely on each other. Of course, following all of these results may slow down a little bit the execution time, may lead to a repetition of work sometimes, but this is the only way we could deliver reliable results and consistent results. And this is the only way to find bugs very easily and very fast and very early on at the development stage. And we actually were, trying out different ways to improve our performance, and we found out that it is very useful to use a very minimum amount of data sets to perform the maximum coverage. So we are always very mindful of the data that we are using in our tests. So I will finish the presentation by going back at the different goals that we set and check on if we met all of them. So were we able to test locally, early in the development process, and without the hassle to do specific setups? Yes. Were we able to integrate our solution with a CI/CD pipelines? Yes, even without the click of a button, we are just pushing our code and it is tested automatically. Did we build a migratable and technology agnostic solution? Yes, our pipelines can work both in the cloud, on-premise. They're working locally over different engines and file systems. Were we cost and time efficient? Of course. Okay, I'm not going to concentrate on the initial cost because there was one to develop, to test this framework. But on the other hand, we experienced a lot of benefits from using a custom-made solution for us, because we could easily scale our solutions without additional cost, and it has helped us very fastly and easily implement and test our pipelines locally. And as a bonus, we found out 2 additional benefits. First of all, by following the approach of testing very early on at the development phase, we minimize the need of a QA engineer who would go somewhere in the development environment and check on if we made some mistakes and then go on and fix them and etc. You remember the first slide. And the indication of that is that we haven't had a critical bug in the last year. So it's kind of an achievement. I hope this was enough to encourage you to develop a similar testing solution yourself. In the previous slides, I gave you a few starting points to start building your own DIY LocalStack without LocalStack. Thank you for attending the presentation.
Thank you, Desi. Actually, I have a question. Did you do deeper analysis of the cost and the comparison of the difference in the cost between building this in-house compared to the using LocalStack, for example?
Well, actually, to be honest, we haven't done that. Because at first place, we never continued using LocalStack. At the beginning, we found, we find another path and build our solution. But if I can, give a rough estimation, probably the cost of developing your own solution, first of all, to develop is fixed. So it is going to cost developers time and, of course, salaries to build it and test it. And of course, later on, small cost to maintain it. But in our case, the cost of maintaining this solution would probably not be so much because it's very simple and well done. But on the other hand, the cost of using a ready solution is not fixed, and it kind of depends on the size of the team and the counts of your pipelines, as I mentioned earlier. So I may be speculating here, but probably at the first year, in our case, having thinking about our pipelines and the size of our team, probably it was going to cost the same, but I think the difference of the cost would be visible at the second year when the second year for many reasons, like cost-wise. Because our solution increases, there are more people coming, and as I said, when you choose a paid one, this is going to be costly. So whenever you scale, but whenever you're using your custom made, the only cost you would pay is going to be, the maintaining this solution, which I don't believe is so much.
Okay, thank you very much. It was
you.
Quite interesting, and I believe that a lot of people are going to try to implement it by themselves, or try to at least to evaluate the options available on the market and compare them for their use case. Thank you.